like you to get out of this is some common ice erosion mechanisms. The Riprap sizing criteria, at least based on what we use at Corel, stone placement options, and then just some brief examples of where we've actually implemented the ice erosion analysis and potentially an example of how to mitigate for that erosion. Okay, so the two primary ice erosion mechanisms are going to be ice shove, which is basically where the ice sheet will uplift soil layers, usually the root mats, and then what happens is those uplifted layers will then fall back in near the water, and they'll be subject to fluvial forces. So when there is open water, they're subject to erosion. This certainly happens in quite a few places, especially where there's long fetch lengths and that ice shove can be pretty significant. And then you have what we would consider just the shear stress on the banks. And so this can be due to fractured ice movement. It can also be associated with the increased velocity if you have an ice jam or an ice jam release or a jave. So there's a couple different mechanisms that can increase the shear stress on the banks, and so it just depends on the specifics as far as what you may want to consider for when you're looking at this sort of analysis. So ice shove. Perhaps this is something that you've seen or had to deal with in the past, but essentially the ice will meet the shoreline, and then it basically, instead of riding up on the shoreline, it basically has the compression force that pushes the root mat up. And then, as you can see on the picture on the left there, what happens as the ice recedes, the vegetation and the root layer actually will fall back in and again be subject to fluvial processes or even wind processes. And so this is a huge erosion issue in many areas. And in fact, the Great Lakes deals with this, areas in the upper Midwest. And so I think this is one of the primary concerns with losing, in particular with losing agricultural land where there's a water body next to it. Ice shove can, as I mentioned on the Great Lakes, can be pretty significant. So not only do you have the erosion, but in this case, you have actually the shove causing direct damage on structures. So we just throw this picture in, it's an old one, but it's pretty significant as far as when you have extremely long fetch lengths like you do in the Great Lakes region, the shove can be enormous as far as how far the ice sheet will be pushed up. The increased shear stress. So I showed these pictures yesterday, but just kind of wanted to reinforce this. So you can see on the picture on the right there how much sediment is included in that, basically in that shear wall there. And I think this is fairly common for a lot of rivers where, and if you've ever been out there during breakup, the fractured ice is actually sitting there just grinding away on the shoreline, and it really has nothing to stop it unless you have like bedrock exposed or something, because it will grind through just about any sort of shoreline material. And you can see as often you can see in these photos, extremely large vegetation, large trees that they end up getting failing and end up getting entrained in the ice run. I was going to show this one. I don't know. Okay, well, the video didn't quite work, but that's okay. For time purposes, we'll just keep going here. But if you have a chance, you can go look at this if you're interested in the slides. But essentially, there's a video of showing the kind of shear stress that occurs along the shoreline as the ice run is occurring. And this happens to be the Huntington River in Vermont. So Chandler's probably been there during this particular breakup, and just thought I would show an example, but we'll keep going for time's sake right now. So riprap sizing. This is one that we get pulled in to answer questions on all the time. And I think for two reasons. One, because Corel did probably some of the foundational work on this, as you can see in a couple of the reports here. And two, because people just have a really hard time believing when we tell them how large a stone they need to protect against ice plucking. And so sometimes they want to ask us firsthand if that's real. But in any case, these are two kind of foundational documents where the lab experiments were done to estimate the actual stone size that's needed to prevent ice plucking. And so that these are available. I know that this 96-12 was available online. The other one, I don't know if it's actually online or not, but it's a white paper that was done by the folks back in the late 90s. So we can certainly get that to you if you have questions on it. What it includes, though, is the criteria for riprap sizing. Now, I pulled these out, and these figures aren't probably very readable in this situation, but the main point here is that the cumulative probability of failure is based on the ratio of the ice thickness to your median diameter, okay? And then so each slope has a curve associated with it, and as you can see, they're all fairly close, but essentially this gives you what the probability of failure is given an assumed ice thickness, and you can actually back into what diameter of stone you would need. In the 96-12 report, the main items to note here, little or no damage generally occurs during write-up. Most riprap damage occurs during pileup events. And so if you want to accept a probability of failure of 15% for your riprap, what usually you would estimate is the median stone size needs to be 2 to 3 times the ice thickness, which if you start doing the math in your head, for those of you that are probably doing it right now, those are large stones depending on exactly, that's a large diameter depending on where you're thinking about putting armoring. This plot out of the 96 report, the 96-12 report, I just bring your attention, it's slightly different. They use the ratio of ice thickness to your D100. We generally don't follow this one. We generally follow the D50 criteria, but just so you know that there is a slight difference between how that's laid out there. So when people start doing the calculations for the size of stone size they need, their next question is, okay, well, how do we not increase our probability of failure, but still not have to get these D50s that are 6 or 7 feet in diameter? So what we tell them is that stone placement can be a criteria that will help that. So there's essentially 3 different types of placement. You have random placement, selective placement, and special placement. So the random is just as it sounds. Essentially, you're taking the riprap out there and just putting it along the shoreline. However it falls, it falls. Selective placement, you're actually interlocking the stones, and while the stones themselves are likely random shapes, you're going to lock them in as best you can. And then the special placement is actually using selective placement, but it goes a step further where your stones probably have more uniformity in shape, and so you can lock them in even better than you would if they were just quarried stones that have random shapes to them. So the special placement, just kind of an example, you're probably going to do that with at minimum your capping stone, but you may have to consider how your other layers interact with the capping stone. So it's certainly one of those things to look at as far as the cost and what your design is actually going to be. This happens to be a breakwater for I believe Buffalo Harbor. So the ice thickness and the wind fetches are enormous there, and so I think they spent a lot of time with sizing and keying in that capping stone. Here's an example of special placement. You can see how the stones are keyed in and interlocked here. And while certainly that increases the cost of construction, it may be well worth it than trying to source the stone size that is necessary to use random placement. So that's something certainly to consider as you're looking at material sources and or costs. So let's just step through a quick analysis here, or an example analysis. So a workflow that you may want to consider is look at the design criteria that is applicable to your state or locale. And then you'd want to size the protection, the shoreline protection, based on the ice conditions, the criteria that we were just talking about. But it's also probably worth doing a force analysis on that, because instead of having to armor with the same diameter for miles and miles, perhaps you can do a force analysis to give you a better idea where you need to focus that. And then also another determining factor is, of course, you need to look and see what your maximum stone size is. Because I know, talking to Omaha District, when I told them that they needed a D50 of 6 feet for the Yellowstone, they just laughed because they said that, well, there's no place to get that. So they obviously had to figure out something else that they would do. And then determine if special placement or some other conditions are necessary that may help with solving some of the available size that is there versus the failure criteria that we were just discussing. We've done this before, and so what we did was not to belabor this too much, but essentially use the Stefan equation to look at what the average ice thickness is. And so based on that average ice thickness, we came up with what we would say a duration thickness analysis would be for this particular water body. And then from that, we did a force analysis. So in this case, we looked at both the shear stress of the water flow as well as the wind fetch. So in this case, the fetch actually was a significant force. And so by looking at the force analysis, we were able to relate to Omaha District, hey, there's certain areas where you may want to target your riprap placement, whereas some places it may not be as critical. And what we ended up doing was creating this ice force frequency plot for them, and this happens to be by month. And then they could decide which what's their probability that they want to design to, and I think that was really helpful because instead of just having a single number, they could actually look at it from a probability standpoint and communicate that back to some of the locals as well as the decision makers. I'll just touch very briefly on this, but one of the potential alternative solutions that we have helped in doing some of the analysis is particularly related to ice shove. So trying to force the ice to fail in a bending fashion as opposed to a crushing fashion. And what we've done is, if you have room, you can create these these small islands where it'll promote right up, and that ice will fail in a bending fashion, and therefore won't actually cause a significant shove on the shoreline, leading to substantial erosion. So this is just an example from the Missouri River, which I've showed you a few of the calculation slides from that. that's all I have for this. Hopefully it's close. 15 minutes is not a lot to talk about ice erosion, but probably close to that. Any questions?
Any more questions for Jeremy?